Hello everyone, welcome back to Decking Cards. So today we'll be taking a look at two more problems from the Putnam 2025. Now the general consensus has been that problem set B is even easier than problem set A. So is this actually true? Well, let's take a look at the first two problems. So B1 is a geometry problem and is as follows. Suppose that each point in the plane is colored either red or green, subject to the following condition. For every three non-collinear points A, B, C of the same color, the center of the circle passing through A, B, and C is also this color. Basically, for any three non-collinear points of one color, the circumcenter is also of that color. So we are supposed to prove that because of this condition, all points of the plane are actually of a single color. Okay, so this is my favorite type of geometry problem. It's a bit fun to add some combinatorial flavor to it. So let's dive straight into the solution because it's actually not too difficult. Now, firstly, let's translate or think a little bit about that condition. So one of the implications of this condition is that if let's say we have a green point over here and we draw any circle that is centered at that point, then on the circle you can find only at most two colors of the opposite color, or rather 2 points of the opposite color. And that's because if you have 3 red points, then you will contradict the condition because that 3 red points have the green point as the circumcenter, which is opposite of what we want. So everything on this circle must be green except for at most 2 points. And this holds for every circle that has the green point as its center. This is quite powerful. And so there are many ways to proceed from here, but the simplest is the following. So assume on the contrary that there exists a red and green point. I think this step is pretty standard, so you have the red and green point here. So what I meant by many ways to proceed is from this point onwards, there are actually many ways you can try and deduce some of the other points in the plane and reach a contradiction. So the way I naturally went about doing it is I first consider the two equilateral triangles like this. Now you cannot have red, red, red because then these 3 points are actually on the same circle with this as a center. See the radius here, radius here, radius here. So you cannot have both red. Now similarly, you cannot have all 3 green here because they lie on a circle with the red point as the center. So these 2 points here must be one red and one green. So without loss of generality, let's say it's green on top and red below, then you can continue to make such some similar deductions. So I'm going to now draw this hexagon with all these equilateral triangles, and you notice that this red circle or red point over here, and this is a circle, right? These 6 points lie on the circle, and because we already have 2 green points, everything else on the circle must be red. So we deduce these points are all red. Okay, then same thing, I have this as center now, and I have these 4 points on a circle, this, and this, right? And green here, but I already have 2 red points, so everything else on the circle must be green, including this point over here. And then lastly, I'm going to complete this hexagon over here. Same thing, red center, I have 6 points on the circle. These 2 are already green, so everything else must be red, including these 2 points. And finally, we have our contradiction because with this as the center, we found 3 points that are equidistant from it, so they will have light on a circle with the green point as the center, but these 3 points are red. So contradicting this statement, which means our original assumption here must be false. Yeah, so that's it for problem B1, and it's actually quite straightforward in my opinion. Like, you start with this and then you do some deduction. There are many ways to reach the contradiction. Okay, let's take a look at problem B2, which is another analysis problem, but not to worry, it's actually quite manageable as well. So the problem is as follows. Let f from 0, 1 to 0, infinity be strictly increasing and continuous. So something like this. Let R be the region bounded by x equals 0, x equals 1, y equals 0, and y equals fx. So basically, x equals 0, x equals 1, y equals 0, and y equals fx. So r is basically this part, the area under the curve. Let x1 be the x-coordinate of the centroid of r. So basically the center of mass or center of gravity. I'll give the formula in a moment. Let x2 be the x-coordinate of the centroid of the solid generated by rotating r around the x-axis. Prove that x1 less than x2. Now the centroid might not be familiar to some of you, but basically it means center of gravity or center of mass. So the formula for it is quite easy to remember, which is that basically, let's start at the center of mass first for r, and the x-coordinate is basically given by this formula. And how do you interpret this formula? Well, basically, at a certain location x, the very thin slice, vertical slice, has what mass? Well, it has height of fx and a width of dx. So that mass contributes a x-coordinate of x. So if you integrate that, you basically are taking, over here, you're taking the weighted average of the x-coordinate. You see what is happening here? Basically, your x-coordinate, you take a weighted average of it, right? Your weights are the mass of that thin slice, which is fx dx. So summing that and dividing by the total mass is basically going to be integral in this case, because you're taking infinitesimal thinner and thinner slice. Yeah, so hopefully this formula makes sense if you don't already memorize it. Now same thing for x2, you can kind of quite easily deduce the formula. So basically this time you have rotated r around the x-axis, so you get like solids, right? And at a particular x, you now need to find the weight, which is the mass of that slice of the solid. Now the mass of that is the area, cross-sectional area, times the width, which is dx. And the cross-sectional area is actually pi fx squared. It will be a circle, right? So the pi and the bottom pi sort of cancels, and then you get this formula over here. So same thing, is just the weighted average of the x-coordinates, where the weight is the mass of the slice. Okay, so hopefully these two formulas are now clear to you. And basically, we just follow our notes. x1 less than x2, which means we want to show the following. I just cross multiply. And once you have this, well, the very natural thing to do actually is to combine into a single double integral. Well, because this is just a variable x, right? I can rename this to y. And then basically, y is not interacting with x. So I can bring this y inside here as fy squared dy, and I have a double integral like this. Same thing, I can rename this variable as y and y, and bring this integral inside here as a double integral. And why would I want to do that? You notice now there's many similar terms like x, fx, fy, x, fx, fy, and the difference is a fy and a fx. So let's try and pull out that common factor. So by bringing one side to the other side together, so I have the fx here as an extra term and the fy here as an extra term. So by rearranging, I now conclude that I want to show this. This is actually quite a nice expression. So at this stage, actually, there is a way to see that this is sort of intuitively true. So you will be actually pretty happy that you are near the end. So I'll explain first the intuitive picture, and actually that intuitive picture helped motivated the rest of my equations. But of course, you can skip straight to the equation. But I'll just explain the motivation or the intuition, why this seems very plausible. So basically, you focus on this f part over here. Let's ignore the x, just fx, fy, fx minus fy. Now this is anti-symmetric in x and y, meaning if I exchange x and y, I will end up with the negative value of the original. So in other words, if I have an xy here, and I have a yx, which is the corresponding point after swapping x and y, then the f value here is the negative of the f value here. Now, when it is here, x is bigger than y, so fx is bigger than fy because f is strictly increasing. Then this f value is positive, and this f value is the exact negative of that. Now, let's now add back the multiplication by x. So this is sort of like a weight. But the x value here in the lower triangle is bigger than the x value here because here x is bigger than y and then you swap the y and x, right? So the positive term gets weighted by a weight that is bigger than the exact negative, which means if I pair up points like this, my overall integration over this entire area is going to be positive. Yeah, so that sort of intuitively makes sense. How do we write that cleanly in equation? So this is the clean approach that I found. And basically it's just working around this idea but now in equation form. So the cleanest way I found is let's look at this expression and understand why this is true. Well, over the lower triangle, I do a double integral. Now, lower triangle is where x is bigger than y. At the same time, fx is bigger than fy because f is strictly increasing. So this integrand is strictly positive, so the double integral is positive. And now I just need to manipulate this to end up with this expression. And it is not very difficult to do so. So first I move the y over, I have this. And then if I exchange the x and y like this, you notice my y and x is now exchanged and the y here becomes an x. You should also take note that the area of integration moved from the lower triangle to the upper triangle. And so now, if I move this back to the left hand side, this x and y, I mean there will be a negative sign by moving over to the left hand side, right? Which then interchange this to fx minus fy. So it goes to this expression over here, same expression. But now I'm adding both the lower and upper triangle as my area of integration. So when I move this over, I indeed do end up back with this equation. So that's all for the proof of problem B2. Yeah, so that is also quite a short and sweet problem. Not too difficult, just follow the equations naturally and you will end up with the proof. So what do you think of problems B1 and B2? Are they indeed as easy as what people have claimed? Well, let me know in the comment section below and stay tuned for more Putnam 2025 problems. See you soon.